Hi everyone. Thank you very much for this opportunity. I'm Özgar Diçli from Karacabey Vocational School of Bursa Uludağ University. And today I will discuss how microbial dysbiosis contributes to disease pathogenesis using a One Health perspective. So microbiota is a term that defines all of the microorganisms that live with the host organism, including various species of bacteria, yeast, and viruses. Given the diverse physiological, metabolic, and immunological functions of the microbiota, maintaining a balanced microbial community is essential for animal health just as it's for humans. In veterinary science, evidence increasingly shows that a stable microbiota supports nutrition absorption, epithelial barrier integrity, immune regulation, and resistance to pathogenic colonization in both companion animals and livestock. Moreover, a wide diversity of microorganism species is crucial for homeostasis. Here, this figure shows the substantial interindividual variability in gut microbiota composition. Although the dominant phyla such as Firmicutes, Bacteroidetes are constantly present, their relative abundances differ markedly between individuals. And at the genus level, these differences become even more pronounced, reflecting the influence of host factors such as genetics, age, breed, diet, and environment. The microbiota represents a highly diverse and dynamic ecosystem, even among healthy individuals living under similar conditions. Under normal conditions, the host and the microbiota engage in constant crosstalk that maintains a stable and beneficial equilibrium. Commensal bacteria thrive in the nutrition-rich environment, while the host benefits from their metabolic, protective, and immunomodulatory functions. When this balance is disrupted, whether through the loss of beneficial organisms, growth of pathogens, or a reduction in microbial diversity, the host becomes more susceptible to inflammation and pathogenic invasion. This state of disrupted microbial equilibrium is known as dysbiosis. Microbial balance can be disrupted by multiple factors, such as dietary changes, antibiotics, environmental pollutants, stress, infections, and early life microbial deprivation. These disturbances reduce beneficial metabolites like short-chain fatty acids, weaken epithelial barrier function, and increase susceptibility to inflammation and metabolic disorders in both humans and animals. Over the last 3 decades, many chemicals have been introduced to our daily lives without adequate characterization. These chemicals are used as emulsifiers, sweeteners, surfactants, and preservatives to increase shelf life, and they act as disruptors for homeostasis. In this respect, epithelial barrier damaging agents from the environment also lead to microbial dysbiosis and the translocation of commensal and opportunistic pathogens across epithelial barriers often trigger a type 2 immune response. This response is marked by the dominance of T helper 2 cells, group 2 innate lymphoid cells, and eosinophils. Mast cells, macrophages, and antibody-producing B cells may also participate in this process. In this setting or under continuous exposure, the epithelium fails to complete the repair and seal the barrier, creating leaky barriers, microbial dysbiosis, and chronic inflammation. This biological process causes an ultimate vicious cycle leading to epithelitis, expulsion response, and microbial dysbiosis. Studies in human beings and animal species have associated with intestinal dysbiosis with various gastrointestinal disorders such as inflammatory bowel disease, granulomatous colitis, and irritable bowel syndrome. Moreover, food hypersensitivities, chronic enteropathies, obesity, metabolic dysfunctions, atopic dermatitis, respiratory allergies, infectious diarrheal diseases, and even behavioral alterations through the gut-brain axis can be seen in dogs and cats. In livestock, dysbiosis contributes to ruminal acidosis in cattle, post-weaning diarrhea in piglets, necrotic enteritis in poultry, and impaired production efficiency. In dysbiosis, one of the most common signs is an increase in facultative anaerobic bacteria from Enterobacteriaceae family. When intestinal permeability or inflammation rises, oxygen levels in the gut lumen increase. And higher oxygen suppresses strict anaerobes and instead allows facultative anaerobes to expand. So overall, oxygen becomes a key factor that disrupts gut homeostasis and drives dysbiosis. A One Health perspective shows us that dysbiosis is not species-specific. Humans, animals, and their environments share similar pathogenic mechanisms and risk factors. Therefore, interventions should also be integrative, such as microbiome-based therapies, improved nutrition, reducing environmental toxins, and monitoring microbial health. Interestingly, recent evidence shows that dog owner pairs exhibit simultaneous allergic traits with a higher risk associated with urban environments, and they share some skin microbiota. This suggests that dogs and humans are predisposed to allergies due to similar risk factors. However, the absence of shared bacterial taxa that predispose to or protect from these allergies implies that factors other than environmental microbial exposures could influence the differences, possibly because furry dog skin and furless human skin selected different microbial taxa. To conclude, the microbiota is fundamental determinant of health. Diversity of microorganisms is one of the major constituents of healthy microbiome. When microbial balance is disrupted, it can initiate or worsen numerous diseases. A One Health approach connecting human, animal, and environmental health offers the most effective framework for addressing dysbiosis-related challenges. These perspectives enable the development of more efficient treatment. Thank you all for your attention.